call chemical arithmetic, this funny word called stoichiometry. Some people find it intimidating, but hopefully we'll make it manageable. How do we approach this? We will need to look at our learning objectives for this chapter to see how that is going to be approached. The learning objectives for the Chapter 6 topics are here. We will begin by discussing things about how to write and balance chemical equations for simple chemical reactions, and we'll progress to these other topics gradually. All right, for the first recording here, I want to talk a little bit about chemical symbols. And we've seen formulas of compounds. We've talked about how to name compounds. And we need to make clear what we're referring to when we write a chemical reaction. So if you see hydrogen, 2H2 as a gas, combining with oxygen gas, making water, with 2 in front of the water as a liquid, what is it telling us? On a microscopic level, we're suggesting that there's 2 molecules of hydrogen, as shown at the left here, reacting with 1 molecule of oxygen gas that yields the 2 molecules of liquid water. On a microscopic level, that's exactly what we think about happening here. However, we use these symbols in more than one way. We will also talk about this on a macroscopic level, where 2 moles of hydrogen gas are going to react with 1 mole of oxygen gas to give us 2 moles of liquid water, remembering that a mole is just a proportion in proportion to the number of atoms or molecules. You can talk about molecules or groups of molecules, and groups of molecules in the quantity of moles is where we'll tend to describe. When we get to further parts of this chapter, we'll understand how you can explain that you can measure it out in terms of grams, because moles are related to grams in formula weights and molecular weights. And for this particular example, 0.56 kilograms of hydrogen gas will be sufficient to react with 4.44 kilograms of oxygen gas to give us 5 kilograms of water. Yes, those should add up because you're combining all of the hydrogen with all of the oxygen to make water. Sometimes those are too obvious, but we haven't even looked for them. But how we get those kilogram values, we'll come back to that. But those are macroscopic things, things that you can actually look at and measure, as opposed to counting individual molecules, which you can't. So once we understand what these chemical symbols mean, we're going to use them representing various chemical equations. We're going to balance these chemical equations to make sure that they represent things in a written fashion that correspond to what's happening on a microscopic level. So we've seen a few examples of reactions here and there as we progress through the chapters so far. For example, if you've got 2 hydrogen combining with oxygen to make 2H2O, what does that tell us? How do we know that that makes sense? You have to count the parts and realize that there are 4 hydrogens and 2 oxygens on the left side of the arrow, and still 4 hydrogens and 2 oxygens on the right side of the arrow. If you're combining, in the second example, sodium with chlorine, and remember chlorine is diatomic, which is why it's listed as Cl2, you can hopefully readily identify that there are indeed 2 sodium atoms represented and 2 chlorine atoms represented on the reactant side, as well as 2 of each on the product side. The third example here is a little more complicated looking. If you have to remember what it's called, there's mercury 2 nitrate combining with potassium iodide to make a mercury 2 iodide compound and potassium nitrate. This takes a little more sorting out to make sure that it makes sense. And hopefully if it's balanced properly, you should get things all come out the same. So there's 1 mercury on the left, 2 nitrogens, because the 2 applies to everything inside the parenthesis, which gives us 2 times 3 or 6 oxygens, 2 potassiums, and 2 iodide, because it applies to everything in the formula, 2 of each. And on the product side, we've got to make sure it still makes sense. If the reaction is balanced, it should. And we should still have 1 mercury and 2 iodide atoms. So far, so good. And we still have 2 potassium right there, and 2 nitrogen, and 2 times 3 gives us 6 oxygen. So it all checks out, and these are indeed balanced equations. So we need to work on how you can carefully balance chemical equations given the information about reactants and products. The idea here is that we want the equation to reflect the fact that we adhere to the law of conservation of mass. And so in a balanced chemical equation, the numbers and kinds of atoms on each side of the arrow are going to be equal. when it is balanced, just like the sodium chloride example on the previous slide. So if you're counting them up, you'll want to count each side and be systematic, because otherwise you miss things. The left side has 2 sodiums, 2 chlorine. The right side has 2 sodium, 2 chlorine. We'll do more examples to make sure we're getting lots of practice to make sure we understand how this is done well. The example with the mercury nitrate and the potassium iodide is shown in the pictures at the bottom of the screen, making mercury 2 iodide and potassium nitrate, and that begins as a aqueous mixture. So how do we know that it's balanced? We've got to double check these things carefully. So the left side, we're going to look and see 1 mercury, 2 nitrogens, 6 oxygens, 2 potassium, 2 iodine atoms. On the right side, then we'll have again 1 mercury, 2 iodine, 2 potassium, 2 nitrogen, and 6 oxygens. It might be in a different order, but it's all the same things, and the equation should be balanced as we expect. So if we're going to approach unfamiliar examples or new examples as we go along, how do we do these things? And there's some guidelines. It's not a foolproof thing. There's not one hard and fast way, but there's some guidelines here. And sometimes trial and error works, but in a general sense, this is what you'd like to do. So you're going to start by writing an unbalanced equation using correct chemical formulas for each reactant and product. We can't say it more emphatically enough that the correct chemical formulas have to be used here for each reactant and product, which is why we've spent some time talking about names of compounds. Unless you've named and put formulas together correctly, the balanced equation will be meaningless. So let's try an example. CH4, that would be methane, as you might recall, reacts with oxygen, and it's going to make carbon dioxide, easy name, and water. And this is just the unbalanced equation with correct chemical formulas, and we're not going to change formulas ever when we balance a chemical equation. So step 2 is to find suitable coefficients, aka these numbers that we put in front of formulas to tell us how many of the formula unit of each substance is going to be required to get the equation to balance to reflect conservation of matter. So what we want to do now is insert a 2 in front of the oxygen on the left side, because in the first example you can tell that there's 2 oxygens there, and we have to certainly have more because we aren't done yet, and you're going to have more than just 2 there, because CO2 has 2 and then there's 1 more here. Well, that doesn't come out even, so they're going to need to be a 2 in front of water also to end up with an even number of oxygens. And when you do that, hopefully things are going to check out. Okay, so let's follow through the steps. So when we do these things, sometimes we end up with numbers that are multiples of one another, and so we want to reduce to smallest whole number values. That is our goal. Sometimes you'll end up with situations where it looks like you want to end up with a fraction, but generally we'll want to stick to whole number values. And if need be, we'll divide everything by a common divisor. So if you had ended up with this value, this example here, so I just adjusted the coefficient on methane. It was incorrect for a moment. So if you ended up with a situation where your numbers were all divisible by 2, that wouldn't be the desirable endpoint. So what would you do? You take and divide everything and end up with smallest whole number coefficients as shown at the bottom. When you get done, it just doesn't ever hurt to be really careful. You should always recheck your answers because we sometimes miss things. And until you are super proficient with these things, it's really, really wise to give yourself the benefit of rechecking things. So make sure that you count it all up and see that it adds up to what you expect it to. When it's done correctly, then we'll notice that the left side should have 1 carbon, 4 hydrogens, 4 oxygens. The right side should have 1 carbon, 4 hydrogens, 4 oxygens, just as we intended. Let's look at some other examples. People sometimes dislike these conceptual diagrams, if you will, where we have nothing that's named but just use colors. And if this color vision is an issue for you, that's not going to be helpful. But I think this one's not too bad because it's red and blue. So what are we going to do? We're going to write a balanced equation and see how that makes any sense here. If A is red and B is blue, A apparently occurs as pairs of atoms, so we're going to say it's A2. And it's going to combine with B, which also comes in pairs, so we're going to call that B2. And it's going to create something new, where you have 1A and 3B. So this, again, it's a combination, chemical reaction, new combinations of atoms are going to result. And in order for this to come out even, we're going to kind of go back and forth until we make sure we've settled it all down. So we start with an unbalanced equation with correct formulas. Got that. So now what do we have to do to get some coefficients that make sense? Well, to begin with, you have to have at least the same number of A on each side. Right now, that means you're going to have to add a 2 on the right side. But when you do that, you have a total of 6 B atoms on the right side, which is not quite going to come out even until we add another value on the left. And so if you add the 3 in front of B2, there's 6 B atoms on the left. So on the left, you have 2A, 6B. On the right, you have 2A and 6B. Well, that was easy enough to say. Notice that the picture diagram shows that you have 6 molecules of AB3. Well, that's not the simplest whole number ratio for this particular equation, but it doesn't mean that it's incorrect to say that you had more, because apparently we started off with 3 molecules of A2 and 1, 2, 3, 4, 5, 6, 7, 8, 9, right, molecules of B2, making 6 molecules of AB3. You could have started there and then simplified it, but we didn't have to do that if we just started from the formulas and add them up to make sure that parts come out left and right. All right, that wasn't too tricky. But it's worth talking about how more than one representation can be correct, but we're always aiming for the simplest whole number ratios. Okay, here's another one with red and blue, A and B. A this time, molecule A is by itself, combining with molecule B, which is diatomic. And the product is having 2 of each, so it must be A2B2. What geometry they're in is not the point here. We don't have to answer that. And so what do we have to do to make this one come out even? Well, apparently not a whole lot, because you have to have 2A to combine with B2 to end up with A2B2. Nothing very tricky there. You could count the spheres here, and it should come out the same, but that doesn't feel very important right now. One more, red and green. Uh-oh, this would be really challenging for somebody like my son who doesn't see those colors well. So if A is A2 here, combining with green B, what are they combining to make this time? So A is the red ones. Apparently you're going to have BA3 as a result. And so how do we have to do to make this one come out even? Well, the B's look fine until you realize that your A's are going to have to be adjusted to get there. So let's put 2 in front of the number on the right and for the formula on the right, because you're going to have an even number of A no matter what you do. The consequence of that is that you have a total of 6A so far. And if you put 3 on the left, that'll give you 6A there also. But now we have to have some more B. So let's put in 2B here. And so 2B on the left and 2B on the right. All is good. That was not very tricky. All right, so here's another one that's altogether different. It's going to be propane. So we're going to see what we need to do with this. C3H8 is propane. If you might recall, we learned that hydrocarbon earlier, the alkanes, the 3-carbon alkane. You probably can't tell what it is from the picture, but they're telling us that's propane. It's going to react with oxygen. And yes, it's a gas, and propane would also be a gas, but that's not the point of the balancing equation right now. I'll just put that in for the moment. And apparently the products are at the top, CO2, carbon dioxide, and water. This is called a combustion reaction, and this is very classic products for a combustion reaction. You should always get CO2 and water, assuming the reaction is taking place with plenty of oxygen. All right. Plenty of oxygen, otherwise you get things like nasty carbon monoxide poisoning, but let's try to avoid that kind of circumstance. All right, now, balancing the equation. So we got the reactants, check, and the products, check. Now what do we have to do to balance this? So you kind of do a little bit of trial and error. It's typically helpful to just start from the left and work across so you don't miss something. And I would see there's 3 carbons on the left, and now you need to have 3 carbons on the right, so stick a 3 in there. And so far so good. Hydrogen has 8 on the left, 2 on the right. Well, that's not too hard to fix. Now you have 4 times 2, which is 8 hydrogens. Hydrogen and carbon look fine. But now we have to figure out what to do with oxygen. So on the left, you only have 2 oxygens so far. And on the right, you've got, well, let's see here. We've got 3 times 2 is 6 oxygens, plus 4 times 1 is a total of 10 oxygens. Well, that's not nearly correctly balanced yet, so apparently we need to have quite a few more. If they come in pairs, the coefficient of 5 will give us a balanced equation. So on the left you have 3 carbons, 8 hydrogens, and then 10 oxygens. On the right you have 3 carbons. 6 oxygen plus 4 oxygen is 10 oxygen, and 4 times 2 is 8 hydrogens. Which way you whether put carbon or the symbols or the numbers in front is all arbitrary as long as you see where you're going. Oxygen and 0 look the same, so be really careful how you read those. It doesn't always make any sense when you have oxygens that look like zeros. Be careful. Okay, that one wasn't too bad. So here's another way of looking at it. If you've got C3H8 is your propane reacting with oxygen, you've got 3 carbons, 8 hydrogens, 10 oxygens. On the right, you have 3 carbons, 8 hydrogens, 10 oxygens. All right, enough for talking about balancing equations for now. I hope those are helpful to you. Work lots of examples. The more practice you get, the more familiar they are. Ask questions as needed. See you in class.